Kepler, through his data, developed three laws that every planet moves in an elliptical orbit with the sun at one focus. Now, I get it. The sun isn't this off center, okay? This is just a kind of like an exaggeration of it. The sun isn't perfectly center of where we're spinning. It's a little bit off center, but what we need to know from that is that as a planet moves, and if we were to draw lines denoting each time period, so if I said from 1 to 2 to 3 to 4 to 5, and all of these different time periods, that section A and section B and section C, if they have the same area, if all of these different sections have the same area, then the time to get from 1 to 2 is the same, as the time to get from 2 to 3 is the same, as the time to get to 3 to 4 is the same, which means these are really skinny over here as they go out farther, because most of the area is made up in the radius of travel. Whereas over here, a smaller radius, that means the time period to go from here to there is the same as from here to here, which means it has to be flying faster, right, to cross that, which kind of makes sense, because if we're farther away, we're slow, and then as we get closer, we start to speed up to have enough velocity to exit back out, or else we get sucked into the sun. We have to have enough speed to make sure that we maintain a pathway that gets us out. So that's Kepler's second law, that the time period between each of these intervals is the same. The one that's gonna ring important to us as Kepler's third law, and that the square of a planet's orbital period is directly proportional to the cube of its average distance. So let me put this in math terms, because that's the way my brain thinks. The square of the orbital's period is directly proportional to the cube of the radius, right? The average distance to the sun. And so even though he started drawing these weird ellipses like this, he said, okay, well, this average radius that it is on average about, that's what we're using over here, okay? And this actually makes sense, because we could prove it what we know using today's equations, but you got to remember, he didn't have these equations. In fact, this is where the equations that we use come from, okay? So what's nice is, just like Newton's laws, what's the Newton's laws that we use mostly up to now, even this, including this point? F equals ma. If this is Kepler's law, then we can actually use Kepler's law and treat it as like, you know how I'm always like, you've got to show all of your work, even though we know that this is the equation that we're trying to get to use. Right now, this is a law, so we're gonna take some time and prove it, but you can start from here. Okay, you can start with t squared over r cubed. Okay, t squared over r cubed. How did they get to that? You know that the force of gravity, it's gonna be this. The force of gravity is how we spin around the sun. Force of gravity is the centripetal force, right? What did we break that down into? Force of gravity. What's universal gravity? And then the force centripetal is, right, ma or mv squared over r, right? I'm going to rewrite this just to make it level. m1, m2 over r squared. Now this m is the orbiting object, right? And then m1 will be the central object then, I guess. So I can cancel out a couple things. What do you want to cancel out? What? So the orbiting mass, the one that's spinning, and one of the radius. One of the radii. We also, and have done this before, where we have that v equals the distance of a circle over T. I like it. Distance over time. What if we plug that into that V right there? What do we get? We get G MC. I'm writing the left side right now. G MC over R squared equals. I'm just going to have to. We canceled out those two. So it's just V squared, right? Oh, yeah, you're right. Good. Good catch. V squared on this side is going to be 2 pi R over T. And then we're going to square that whole term. When we square that whole term, what ends up happening to it? We're going to break it down differently. At this point, you're used to like square rooting both sides. What if instead we just distribute out the squared? GMC over R equals, what's 2 squared? So we have 4 pi squared R squared over T squared. Now, to get it to look like what Kepler proved, we're going to move our R's and T's to the left and the G and the M to the right. So I've got 4 pi squared over G M is equal to T squared over R cubed. Oh, hey, look, that was a T squared over R cubed. All I did is I cross multiplied, I crisscrossed applesauced and said, hey, look, I want to get all my R's and T's to the left. The G and the M went to the right. Okay, so I just switched places of those two bubbles. Some things. So not only is T squared over R cubed constant, but for our solar system, we could say that's the same thing as 4 pi squared over G times the mass of the sun for us, right? That's the center object for our solar system. And that would equal T squared over R cubed for any of the planets in that solar system. So the Earth, we go around in 365 days with the radius of 150 million kilometers. So you could say that's the ratio of 4 pi squared over G times the mass of the sun. Now, Kepler didn't know the mass of the sun. He didn't have a G value. In fact, what we did is we used Kepler's equation to go find those based off of like the greatest common factor of all of the planets and how we measure kilograms. And so there's some more math involved later on, but this is what we knew. Okay. GM was just a constant for him. It works out kind of well because, again, our Earth, we're not that skewed. We're mostly circular, a little bit elliptoided. All right, so here's in general, any system of satellites, the ratio of T squared over R cubed equals the constant for that system. And then, common errors. Using Kepler's third law, we have to compare orbits with the same center. So if they have different attracting centers, then it doesn't work. So here's the example. The Earth's moon versus Mars. Why is that a no-no? What's the center of the moon? Earth. What's the center of Mars? So they don't have the same center. All right, they're spinning around different objects, then it doesn't work. All right, even if we're in the same solar system. All right, so sample. A moon of Jupiter is nearly circular orbit with a radius r and orbit period of t. Give it an expression for the mass of Jupiter. So our equation was 4 pi squared over g ms equals t squared over r cubed. Which one do we want by itself? Give an expression for the what? Right. And I said the mass of the sun, but is this the mass of the sun if we're talking about the moon of Jupiter? No, that's Jupiter. All right, so I'm looking for this right here. How about I move it up that way? So everything else ends up on the other side. 4 pi squared over g t squared. And then I need that r cubed up top equals mj. Does that work out? I moved my r up there, and I moved my t down there when I moved crisscross those two. Swap places. I think that works out. Does it answer a question? Give an expression for the mass of Jupiter using variables. And the variables I'm allowed to have, 4 is a number. What's pi? So it's just a number? R cubed. We're allowed to have that. It's at radius r. We just assign it that letter. Period t. And g, what's g? 6.67 times 10 to the negative 11. So it's just a number. All right. This is good for an answer. All right, Neptune is an average distance of 4.5 times 10 to the 9 kilometers from the sun. Estimate the length of the Neptunian year given that Earth is 1.5 times 10 to the 8th kilometers from the sun on average. Guys, everything in the solar system has the same constant value. How do you want to set this up? T squared over r cubed for the Earth would have the same constant value as t squared over r cubed of what planet? Sorry, Neptune. I just didn't know what subscript I was writing. Neptune. Because it could have worked for any other planet. I was about to put J for Jupiter. T squared over r cubed. What's the t time period of the Earth? 365 days. I'm going to put 1 year just for ease sake right now. 1 squared. What's the r of Earth? 1.5 times 10 to the what? 8th kilometers cubed. What is this? 1 year equals 4.5 times 10 to the 9th kilometers. This gets cubed. And we have the time period of Neptune squared. So you're going to have to square root the whole thing by the end. Hey guys, one tip to you. Did I convert my kilometers? No. Why not? Because they cross out. Yeah, they're going to cancel out on both sides. If you did convert, is that a big boo-boo? If you said 1.5 times 10 to the 11th meters, that's fine. As long as you said 4.5 times 10 to the 12th meters over here. They have to match to cancel out. Okay. Same thing with the year. If you did 365 days, your answer will be in Earth days. But now your answer is in Earth years. Or else we should have done seconds technically. Honestly, I've been doing it in days up until now, so I don't actually know what it is in years. It's got to be over 100. Less than 200, I think. 164? 164 years. 164 Earth years. Right? Years would have made sense because that was your starting unit, but in this case, technically we just solved for a Neptune year. Why does that make sense? No, it's not because we're bums. Why does this make sense? Because what? The radius is longer. Neptune is very far away from the sun, not very pulled in by gravity, gets to move very slowly, so it doesn't like fly off. All right, last problem. Problem 3. What we're going to do here, think of a pathway to solve this. Do the following satellites orbit the same central body? what can you measure for all of them? The constant. T squared over r cubed for object 1. Does it match or not match T squared over r cubed for the next one? Yeah. Does it match or not match for the next one? All right. When you get done with that, if one of them does not match, then we know our answer. If they all match, I know it feels kind of repetitive, but at least all you have to do is type it in the calculator once you've got your formula set up. You could also just overtype it if you don't want to change your formatting. But if one of them doesn't match, then that would be the one to mark. If they all match, then you're good to go.